just a quick reminder, the last little piece that I want to remind you about for linear algebra that we'll be using in the next sections is on determinants. Now, determinants are never fun things. The only time it's really easy if when you have a 2 by 2 matrix. So you can only, first of all, you can only find for square matrices. That is, same number of rows and columns. Determinants undefined for non-square matrices. Okay. So what's a 2 by 2 matrix determinant? Those are the only easy ones. Okay, so if you have something like A, B, C, D, the determinant of A, B, C, D, which is often just written as the matrix with straight lines around it. How do you compute that? It is AD minus BC. So you take the product along the main diagonal and subtract the product along the other diagonal. Okay. So that's pretty easy. You just memorize it, that's it. And then remember that you can find the inverse of a matrix. We already knew this. We knew that A, B, C, D inverse is 1 over the determinant times you reverse the main diagonal and take -1 times the other diagonal. Okay. And then that gives you the inverse of a 2 by 2 matrix. So if the determinant equals 0, the matrix is not invertible. Okay. So that's clearly true for a 2 by 2 matrix because you can't divide by 0 and the determinant is AD minus BC. But it's true in general. For an n by n matrix, that is a matrix, any square matrix, let's call it A inverse exists if and only if the determinant of A is not equal to 0. Okay, so determinants are important because they're not, if the determinant is 0, the matrix can't have an inverse. It's not the only reason they're important, but that's one of the reasons they're very important. Okay, so the determinant is a thing we're going to see come up several times in the class in different ways. Okay, the bad part about a determinant is as soon as you get to anything bigger than a 2 by 2, if you try to write down a general formula, it looks horrendous. So I'm not even going to try to write down the general formula. I'm just going to remind you how to do it. And the best way to do it, I think the easiest way to compute it is expansion by minors. We'll learn how to compute the inverse of a matrix by a pretty slick method when we need it, but I don't want to get too far ahead of ourselves explaining to you things we don't quite need in this chapter yet. So to find an n by n determinant, and I'm assuming most of you have seen a little bit about matrices before, so I hope this is just a reminder. To find an n by n determinant, what you need to do is just to expand by minors. Okay. All right, so I'm going to do this in the context of a couple of examples. And I don't want to do this in, let me find the examples that I want to use. Okay. So let me do this in the context of a couple of examples. So let's start with Take a sip of some water. This is hard to keep talking with nobody here. Okay, so let's take the matrix A to B, the matrix 1, 2, 3. 2, 4, 5. And 3, 5, 6. Okay, and I ask you to find the determinant of it. Okay. All right, so what do I mean by expand by minors? Okay, so you have to know, determinants involve alternating signs, plus and minus. So think with every one, and they always have to go, you start with a plus in the upper left-hand corner, and you think of plus, minus, plus. And now it has to alternate. So this will be minus, plus, minus, and this one will be plus, minus, plus. Okay, and you keep that in mind, just sort of in the back of your mind that that's there. And now pick your favorite row or column. If you have one that has lots of zeros, be sure to pick that row or column. And you can expand along any row or column of your choice, but you have to respect the signs that are there. Okay, so what, let's just go ahead down the, let's go down the first column. Okay, so what do I mean by expanding my minors? So I'm going to go down the first column. I take this entry, the 1, and I write it down. And then in my mind, I delete the row in the column containing 1. So I delete this row and I delete this column. And if I place things properly, that leaves me with a 2 by 2 matrix. So next to that 1, that plus 1 I just wrote down, I write the matrix 4, 5, 5, 6, because that's what I see, and I have to take the determinant of that. So that's the 1, 1 minor, because it's the minor you get when you eliminate the first row, first column entry. Okay. Now I'm going to go down the column. The next entry is a 2. The 2 goes with a minus sign, so I have to say minus 2 times. Now delete the row and the column containing 2. This might be harder because it might cover up too much. It's almost too big. Delete the row and the column containing 2. That leaves me with 2, 3, 5, 6. So that's what I write here, 2, 3, 5, 6. Okay. And now I'm going down the column. It's a 3, and that goes with the plus sign. And now delete the row in the column containing 3. That leaves you with the matrix 2, 3, 4, 5. 2, 3, 4, 5. Okay. So now we've expanded along the minors. Okay. And so now what do we have to do? What we have to do is go ahead and take the determinants of these 2 by 2 matrices. So this will be 1 times the determinant of this guy. Notice I wrote these with straight lines, and remember straight lines means determinant of. So this is 1 times 6 times 4 is 24 minus 25. So you want this way minus the other way. And then I have minus 2 times. Take the determinant of this matrix. That's 12 minus 15. It's that minus that diagonal. And then I say plus 3 times the determinant of this guy, which is 10 minus 12. Okay. So let's see, this is minus 1 times this gives me minus 1. This is minus 3 times a minus 2 is a plus 6. This is a minus 2 times 3 is minus 6. And so the determinant of this matrix is minus 1. Okay. So that's what we did. We expanded along minors along the first column. So that means you go down the column and you delete. But you could go down any column. I didn't have to choose the first one, and I could actually use any row. I could use this one or that one or that one. The only thing I have to respect is this alternating sign deal that tells me what since I went down the first column, it had to go plus, then minus times the 2, and plus times the 3. Okay. Now, if you have a 4x4 matrix, you have to expand along minors. But at the first stage you do that, you'll get from a 4x4 to a 3x3. And then you have to expand along minors in each of those 3x3s to get down to 2x2, because those are the only ones you really know how to do quick. So as the matrices get bigger, this gets longer much faster. Okay, so you hopefully don't run into many 4x4s, and we hopefully don't run into any 5x5s. Let me do one more determinant for you where you see something. And by the way, since that determinant came out to be non-zero, that original matrix we started with has an inverse. I'm not telling you how to compute it yet, but it does have an inverse. So here's another example. Let's take the matrix A to be the matrix 1 minus 2, 1. And then the matrix 2, 1 minus 2. And then the matrix 1, 8 minus 7. Okay, and then find the determinant of A. Okay, all right. So we start to expand along minors. Let me write my plus minus for you, and I'll pick a different way of doing it. I won't go down the first column this time, just for the fun of it. So plus minus plus, minus plus minus, plus minus plus. And just for the fun of it, let's go along. I'm going to expand along the second row. Minors along the second row. In this case, since they're all non-zero entries, no one way is going to be any quicker than the other. So if there's zeros, you use that row or that column because it'll help get rid of some things for you. All right, so if I'm going to go along the second row, the first thing I have is minus 2, but that goes with a minus. So I have to say minus, minus 2. Plus 2, I'm writing it like that so you can see where I'm getting it from. And now I have to delete the row in the column containing minus 2. So when I do that, you can't. Okay, you have to imaginary do that. My finger's too big, and so is the pen. It'll delete it. I'll have 2, 1, minus 2, minus 7. So that was 2, 1, minus 2, minus 7. Okay, so I said I'm going across the second row. The next one is a 1, and it comes with a plus sign. Delete the row in the column containing 1. That'll leave me 1, 1, 1, minus 7. Okay, and then the last entry is an 8, but that came with a minus sign, so I get minus 8 times delete the row in the column containing 8. That one I can show you. You'll get minus 2, 1, 1, minus 2. Okay, and now we're down to 2 by 2, so we can actually compute the determinants. So here I get 2 times minus 14 plus 2 plus 1 times minus 7 minus 1 minus 8 times 4 minus 1. Okay, so this is minus 12 times 2 is minus 24. Here, this is minus 8. And then here I get 3. Oh, rats. Either I did, let me check. I thought this was one that was going to give me a singular matrix. But anyway, I'll check the arithmetic in a second. So this is minus 3. And minus 8 is plus 24. Okay, so let me be careful. Let's be careful and double check our work. Let me check that I copied my example correctly. Okay, I did. So if I'm going along the second row, I get minus minus 2, that's plus 2. And then, oops, sorry, knocked my document camera. And then when I delete the row in the column with minus 2, I should have 2, 1, minus 2, minus 7. Then I have a 1 times, delete the row in the column containing 1. That would be 1, 1, 1 minus 7. And then I have a minus 8 because the minus sign goes with the 8. And delete the row in the column containing 8. That's, oh, delete the row in the column containing 8. Here's where I made my mistake. So this should be, sorry, this matrix. When I delete the row in the column containing, I said it right and wrote it wrong. I see now 1, 2, 1, minus 2. 1, 2, 1, minus 2. I transposed the 2 and the 1. I said it right and wrote it wrong. So that changes this determinant here. I have minus 8 times minus 2, that's minus 4. So that's minus, it should be minus 2 and then minus 2. Okay, so that's still not going to change things. Okay, so this one's just not a zero determinant that I thought it was. Okay, because now we have, that's minus 8 times and here is a minus 4 times minus 8 is 8 times, oh, sorry, 8 times 4 is 32. Sorry, pen ran out. 8 times 4 is 32, sorry. It's a little bit late, getting tired. So minus 24 and minus 8 is minus 32 plus 32 equals 0. So when the determinant, so we worked out to a determinant of 0. And so therefore, a inverse will not exist. Okay, that's just an aside. We're going to take that as a fact from linear algebra. We're not going to prove that. But if a matrix has a determinant that's 0, the matrix doesn't have an inverse. Okay, so this matrix can't even hope to have an inverse. Okay, so I think that's enough for our little lecture.